So how can you do this in your head? You can use the exponent rule, which I talked about. When we multiply two powers with the same base, we add the exponents. Here you see it expressed as an equation. Sometimes equations are scary, sometimes equations are useful. So in this case, if you have x to the a times x to the b, it's equal to x to the a quantity, a plus b. We're going to work with powers of 2 in this class because binary things can be switched on and off very quickly. It turns out it's the fastest decision process you can make. There's no ambiguity. It's either on or off. We're going to use powers of 2. So let's try an example. This is what I set up for the study sets, and throughout the lecture I went and made my own questions to try to relate to current topics and something that somebody would pay you to do. So here's, I know it's only the first week, but something actually interesting. You're tasked to specify the data logging period for a 32 gigabyte onboard flash for a car. So this is just like, what's the one that they're always trying to, progressive, right? They want you to hook up wants you to hook up your car so they can see if you drive fast or slow, and then they, I don't think maybe today they're giving you a discount, but I think in the future they're just going to charge you more if you're not driving the way they like. But how big does the memory capacity have to be of that device? It has some flash storage on there for sure. I'll tell you that's how it works. And then they upload from time to time, not all your data, but some, aggregate data. So this car is a Tesla, just to make it cool, and we have 4 sensors. Yeah, it's a 4 sensors per processor. There's 16 processors, like I mentioned last time. Everything has a microprocessor. A car usually has about 50. And each sensor is generating 8 kilobytes per second. Maybe the anti-lock brakes, motion sensor, engine temperature, fuel injection mix ratio, so on and so forth. So what's sought? I always set up the problems like this, givens and soughts, and that's pretty much real world. So if all overheads are ignored, what is the maximum logging period that can be supported? Well, we have 32 gigabytes of onboard storage. Before I go to solve this with you, what would be the sketch in your mind? What is the sketch of the solution? We have some memory capacity and we're generating data. What are we going to do? We're going to make it equality or inequality, right? We can store data up to the time that the capacity is filled. We're generating data at a certain rate. The only thing we need to do is keep track of the units. So we're going to multiply these quantities, right? We have 16 processors, each has 4 sensors multiplied by 4, and this is the data rate, is kilobytes per second, right? And we're going to solve for seconds. That we have 32 gigabytes to fill up. Okay? I like the water analogy for electrical computer engineering. It's very ironic because electricity and water don't mix, but whether you're an electrical engineer working with current and voltage, or a computer engineer and you're talking about capacities and data rates, it's like water filling a container, right? The data rate is the rate of the fluid flowing through the hose that's filling up the container. The container in this case is the onboard flash, and this is the data rate. So we've got to calculate the data rate. So let's do that. We're going to determine the number of bytes of data being generated. So what's the data generation rate? As we mentioned, there's 16 processors, just like I said, 4 sensors, and 8 kilobytes per second per sensor. You end up with, now this is the cool part, I asked you to memorize, and I don't expect you to have it in 30 minutes, but what power of 2 is this? This is 2 to the 4, right? What is 4 is 2 to the 2, and this is 2 to the 3. Kilobytes, what's a kilobyte? 2 to the 10? Turns out it's 2 to the 19. How did I get that so quick? 2 to the 19 is 2 to the 4 plus 2 plus 3 plus 10. Now, in human terms that we use every day, 2 to the 19, is that like the number of seconds in the universe, or like, or 2 to the 19 is about what? Exactly what? Close to a megabyte. It is exactly. It's close to a megabyte. You're exactly right. And how close? 2 to 20 is a whole megabyte. So if you take away 1 bit, you cut it in half. It's half a megabyte. See that? You, Johnny, on the spot. You look brilliant in the project meeting. Everybody else is get their calculator out. We want UCF to, my goal, I'm totally serious. I want UCF to be number 1, and that's my pride, actually. I want you guys to learn and be smart. I'll tell you all the tricks that I know. Okay, yeah. Good question, yeah.
On the test
Yeah.
They keep it as 2 to the 16 seconds. I know you said your tests are multiple choice.
Sometimes I may ask for powers of 2, and sometimes I may ask for the exact value. I think you should be able to do both. So, but it will specify, to answer your question, it will specify, there won't be ambiguity. I'll tell you, express it as a power of 2, or express it as an exact decimal number, and you'll see the choice, 16,384 or whatever. In this case, it's going to be a 1,480,000, so it's going to be like a 512 something thousands, Okay, and next we have, this is the data generation rate in bytes per second. Everybody good to hear? Now, how long does, this is like the flow rate out of the hose, and you have a continuous, you're generating this many bytes per second, and you can hold this many gigabytes. How long does it take to fill up that container? Well, that's going to be the capacity of the memory, and it's going to be how long you can run, how long of a trip. So in this case, we have 32 gigabytes. Remember, right? We have kilo, mega, giga. Just remember, kilo, mega, giga. Kilo is 2 to the 10, mega 2 to the 20, giga is 2 to the 30. So 2 to the 30, right? And how many of those 2 to the 30s do we have? You have 32, which is 2 to the 5. So 2 to the 5 times 2 to the 30, right, is 2 to the 35, divided by 2 to the 19, as we solve for here. How do you take 2 to the 35 divided by 2 to the 19 without a calculator? You subtract. And lo and behold, we get another power of 2, 2 to the 16. Okay, and you're going to say, well, I didn't memorize that one. I don't want you to memorize it. 2 to the 16 is what? 2 to the 6 times 2 to the 10. What's 2 to the 10? 1K. What's 2 to the 6? I do ask you to remember that. 2 to the 6 is 64. Awesome. So you end up with, this is actually 65,536. What is that in human terms? Well, this is a lot of seconds. So human beings don't do good with big numbers, which is kind of the takeaway of today's lesson. As computer engineers, we work with nanometers. Okay, especially electrical engineers, you buy Intel, it's a Broadwell processor, okay, that's in that laptop. It's 14 nanometer technology. A nanometer is nothing, okay? Actually, 1 nanometer is so 5 nanometers is about 18 silicon atom diameters. That's nothing to build a transistor out of. Up to what? We work with terabytes, which are huge quantities, okay? But human beings are not that good with big numbers, so we like to convert these to things that we can work with, and I'll give you some examples and some really useful ones to do that. So in terms of hours, that's about 18 hours. Any questions on solving this problem? There's a problem exactly like this with different setup, okay? I think I did a smart grid or something as a study set problem. If I cover it in the lecture and we cover it in the study set, it's a good thing to choose to learn because there's a high probability it can be a quiz question. But I think you guys can handle this. I know you can handle it. And I want you to not only handle it, to be able to understand why the answer comes the way it is. Check your work different ways. Have it make sense to you. How do we get there? You have to get there iteratively. You look at the problem first, you read it, you get the kind of flow, you plug in the numbers, and then you go back and say, what do those numbers mean? Why is that right? Is there another way? Challenge yourself. Is there another way to understand this problem? Okay, and we can think of this in terms of, I like the water analogy of filling up a container because that's exactly what's happening. We're filling up this flash with bits. Okay, so exponent rule is a big help for us. We're going to try another example in a second, but it allows us to work with these very large numbers and very small numbers, okay, in the same equation. And the key thing to keep in mind is when we work with powers of 2, it's only bits and bytes. Okay, if you're going to work with exponent rule with gigahertz, megahertz, nanometers, it's going to be power of 10. Okay, so let's go to the other extreme now. It's the data warehouse. It's a good area of hiring these days, and you want to go get some of those tasty shrimp at Google's buffet. You can get a job there. We have a lot of our students, actually had some in my lab that interned at Facebook. And suppose, what do they do over there? Well, Google Data Center has 4 data warehouses, so many servers in each warehouse, and so many nodes per server, and there's 1 terabyte per node. And this is not exactly how they do it, but for the first week, suppose that they sell space on each other's and they back each other up. Amazon mirrors a copy uncompressed, which is the only part that's not realistic. We're going to see Google data center soon. You'll actually see some real capacities and things. Suppose here in this problem, they transfer an uncompressed copy every 3 months to back up. How many bits per year are transferred from Google to Amazon? Simplify your final answer. We'll proceed the same way we did in the last problem, okay? The solution will be to calculate the storage capacity of the data center in bytes and then convert bytes to bits, okay? So we have 4 data centers, 128 servers, 124 nodes times a terabyte, and we get units of bytes here, and we end up with 2 to the 59 bytes, which is again half of an exabyte. It's a huge amount of data. So half an exabyte of data is transferred every 3 months. You see any powers of 2 and 3 months? Because it's asked for annually. Bits per year. 3 months is what? 1 over 2 to the... How many months in a year? 12. And 3 months is 1/4. The amount transferred, right? We're going to do what? Okay, we're going to start with this. This is so many exabytes, right? And it's done 4 times per year. So we're going to multiply times a 4, which is 2 to the 2, right? So you can add again, and you end up 2 to 61, or 2 exabytes per year. Are we done? Well, the question asked for bits. Okay. Well, then why did I start with bytes? Because the storage of each disk drive was in bytes. If I convert bits to bytes, no problem. 8 bits per every byte, and 8 is a power of 2. You're going to say, well, I just made up this problem, powers of 2. I did, but that's how they sell these things, because they're in racks, and if you want to double it, they sell you 2 racks, so these powers of 2 keep coming up over and over and over again. You can be like me and say, I'm not going to learn that because I just don't feel like it, but it's just like calculus the first day. Derivative is going to keep coming up. Powers of 2, the whole course. Just memorize 2 to the 0 up to 2 to the 10 when you have time the next week or 2. So that's an amazing amount of bits, right? So if you click here, I put some of these videos. Whenever I say FYI, you can de-stress. It's not part of the quiz. It's not part of the test. It's something to make it real and kind of show you. Usually they're a minute or 2, a few minutes. Let's take a look, see if we have internet connection.
Our first step,
very loud.
The networking room. It's like air traffic control. Every time a user asks Google for something, that request is first routed here.
It's the first week. We'll get more technical as we go.
How many servers?
So today we have 55,200.
The sheer size
55,200.
of the place is breathtaking. Employees must wear earplugs to protect their hearing from the constant whir of...
And this is a couple years old, those videos.
So each of these servers basically is like a PC, except somewhat more powerful.
It's exactly like a piece of...
Those servers goes down. We saw firsthand what it takes to repair or replace them. Okay. Right here.
Big area of hiring, okay? Data centers, big data.
Energy hogs.
This is a key thing. They want us to reduce the energy because it's money and the environment.
On our tour,
We're going to talk about it a lot in this course.
how they were reducing their carbon footprint here at the data centers. That's because the company is very protective of its green image. According to Wired magazine, Stephen Levy, he has covered Google for years and also got a tour of the Lenore data center.
The opening up of data centers really comes from their feeling that they can't keep this to themselves.
Google reduced a lot of its energy consumption by simply raising the temperature on the server floor from a chilly 68 degrees to a balmy 80.
We're estimating that we saved over $1 billion in the history of Google through these efficiency measures.
At Lenore, Google says only 10% of the electricity is not used to power its servers. Another Google innovation, replacing wasteful air conditioners with a water-based cooling system. But for all of the company's efforts to become energy efficient, a lot of their power still comes from non-renewable sources. The power here is coal.
The power here comes from whatever the local utility.
This is like on the East Coast, South Carolina or something.
Which in North Carolina,
North Carolina.
is about 2/3 cold.
Facebook's putting one on the edge of the Arctic Circle because it's always cold, and it's good idea.
Renewable energy, now we're
Guess it's heating up though.
eventually to 100%.
Google says this is the only time they'll allow TV cameras inside their server floor. But in an effort to be more open, they say they will put up video and pictures of all their data centers on their website.
It's amazing how all of this works and that it works at all. And the fact that they...
I'm amazed, actually.
It's just amazing.
For CBS
Okay. So, what's the takeaway from this is that we can see bits and bytes using these enormous quantities. These are great areas of hiring, okay? Both designing the data center, maintaining the data center, as well as designing processors that use less energy. We're going to show you a lot of different techniques in this class. As a matter of fact, we're going to do some experiments. I'm going to ask you to trade off some hardware, software trade-offs, and actually try to minimize the energy for a multiplier. We kind of use this multiplier as a case study throughout the class because it's something that's really practical, but you can still get your arms around it in a semester. So keep these things in mind. We'll come back to a lot of these concepts in the course about energy consumption, capacities, parallel processing, data centers. We'll talk about all these. So suppose you want to solve this a rapid solution. You're just going to use powers of 2. When I look at this problem and challenge yourself, practice, I see a bunch of quantities, powers of 2. I see 2 to the 2. I see 2 to the 7, right? 1024, 2 to the 10. What's tera? 4, yeah. Because you go kilo, mega, giga, tera. 3 months, I see a quarter of a year. Maybe it's a little bit much to do in your head, but you can see. I color coded this so you can match this. 2 to the 2, 2 to the 7, 2 to the this so many bits per year. Okay. So powers of 2 exponents can be written directly for many processor design problems. This is a real extreme example, but you can use this when you're working with memory capacities and data buses and so forth. So as I mentioned, human beings don't do too good with these super huge numbers and these super small numbers. I have my own reason kind of why that is. Probably up to just a few thousand years ago, you know, how many apples can there be on a tree? I don't know, 100 apples, or how many, I don't know what's attacking you. And the herd is coming to you, you know, is it 10 or is it 100? That's all you need to know, right? But now we work with billions and trillions of things every day. As engineers, we need to have a feel for this. This is just like barometric pressure to a meteorologist. You know, you just don't trust a meteorologist when he's talking about the hurricane and he says 870, and then he looks, there's 870 on his phone. Is that a big number? Millibars? Is that high pressure, low pressure? You know, when you work with it, you should have a feel. So a terabyte, we already said, 2 to the 40, that's well over 1 trillion bytes. Here's the actual calculations. All right. It's 2 to the 10 times 2 to the 10, 2 to the 10, 2 to the 10 bytes. So it's well over 1 trillion. What does 1 trillion bytes look like? So actually, I made this slide myself, and I actually didn't completely appreciate. I know it's a huge number, but until you see something we can really understand. So we know a byte is about a character of text. How do we figure that out? As we mentioned, a byte is 8 bits, so 2 to the 8 is about 256. Here's something that actually really made it stick for me. So you can buy a 1 tera, I have a 2 terabyte drive right here. We're recording this video. And 10 terabytes is the total printed matter in the Library of Congress, including figures. Okay. Well, first of all, what's the Library of Congress? You see, I pay my taxes, and I know it goes to schools and things, but I don't know what they teach you over there, because sometimes I scratch my head. What's the Library of Congress? I actually asked one time, and it seemed like nobody knew. Anybody been to Washington, D.C.? I used to live in Northern Virginia. It's a great thing about living there. They have great museums and national things. You can go to use them. What is it?
National treasure. Oh, it is, but I've been to D.C.
You've been to D.C. Okay, so that's half partial credit, so you get half. But Library of Congress was the original internet, before the internet. What is Library of Congress? Well, so the idea, congressmen are supposed to author laws that make sense. But in the old days, how would you read up on whatever it is that you're going to write a law about? You went to the library. Library was like Google, like internet. Well, Google was a card catalog. So they had this idea, because they were smart people, they said, let's put a copy of every book ever printed, because there wasn't any electronic anything, in this one place that's pretty close to where Congress meets, and they can walk over there and read anything they need to read and get smart to write these good laws. Of course, then they just go off on a tangent anyway, but everything that human beings know is about 10 terabytes. That's amazing. You can go buy, 5 2-terabyte drives for almost a student's salary. So that's pretty amazing to me. Still, can we make this in other terms that we can visualize? Because these are huge numbers, and we're human beings, we know, are not too good at big values. The federal debt now is getting close to 19 trillion, right? If you had 18 trillion and you want to visualize that, here's 18 trillion. What is that? These are $100 bills stacked up. What is this a picture of? Maybe people in the front row can see. It is a semi-truck. And these are stacks of money. That's 18 trillion. Okay? And those are $100 bills stacked up. So this is kind of interesting. These come up every few years, and people talk about debt and blah, 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 usually election years, and blows my mind. Donald Trump says, oh yeah, we can get rid of the debt by 8 years. Yeah, it's like, let's try some calculations, use some, Suppose, and people say these things, people say, well, why don't we just have a lottery for that, and you want to help your country, you buy a lottery ticket, you might win. All right. I mean, suppose you wanted to pay off 18 trillion, okay? If you had this Powerball style lottery, how long would it take you relative to a car loan, or let's say a mortgage? Maybe can we do it in 8 years? Donald Trump? I don't know. Well, let's try some calculations. Suppose you net 500 million every month. Everybody goes out, even me, and buy a Powerball, right, when it hits 500 million. They say the optimum is around 380 or something, because when this gets too high, too many people buy, and you have to split the pot, right? It's true. But so what do we have here? We have, I was using 17, I updated this number, and I forgot to update this, and I forgot to update. So 17 trillion, yeah, is a power of 10. It's E, we use a capital E for power. 10 to the 12, divided by 500 million. That ends up to be 34,000 months of having that lottery. So how many months? That's in years. I don't think we're going to do it at the end of Donald Trump's term. Whether you like him or not, that's up to you. But I think that's going to be pretty amazing. If you can get an extra 500 million, which is $500 million every month, you still have a lot of months to go. So you're going to say, well, that's a trillion. That's like, we don't see a trillion every day. How about 100 million? Can we visualize 100 million? That's just like 100 megabytes is 100 million. So 100 million, like I just said, Powerball jackpot versus the incremental distance to Los Angeles. And why am I wasting your time with this? Because first of all, it's helping you get this kind of intuitive feel for bits and bytes and megabytes and so forth, but also giving you a technique to visualize very large and small values. As engineers, we have to deal with these. It helps if we know what these mean. So this is, somebody mentioned this to me one time, and it sounded too incredible, and I actually did the math, and it's true. So how many people have driven from Orlando to California? All right, good. Okay, more partial credit. So how long did it take you? Somebody raise their hand. How long did it take you?
About 3 days.
About 3 days. Oh, you're fast. Okay. So think of it this way. The incremental distance from New York to Los Angeles versus the Powerball jack. What I'm talking about is specificity needed. So in other words, if you took the number of, let's say, miles from New York City to Los Angeles, what's that number in human terms? About 3,000, 2,800 something. The chance of winning the Powerball is a lot less than 1 in 2,800, so a mile is too big of an increment, but maybe feet or so forth. So just think of the number of inches from here to Miami. And you picked 1 inch between Orlando and Miami because you're such a lucky person, you can say that's the right value. The way I heard this was if you drop a golf ball from space over the continental US, do you think it's harder to get it in a golf cup or harder to win the lottery? The Powerball. It's almost the same. The number, so it turns out the Powerball jackpot is a 1 in 175 million to 1, okay, and then 2,800 miles. 520 feet per mile. We're practicing our unit factor method, bits and bytes, and big values and small values. That's how many inches versus the odds. Okay, it's like picking a particular inch between here and Los. You drove it, right? There's a lot of tumbleweed between here and Los Angeles. If you can say, satellite and the golf ball, and it goes right in the cup. That guy's good. He's lucky, right? So, what's the point of this when we talk about terabytes, especially, or even gigabytes? These are huge quantities of information. And we talk about gigahertz. That's very fast on human scale. A nanosecond is nothing. I'll give you a way to understand that. Okay. So if you wanted to go from 175 million to a trillion, you still got 5,000 more to go to get to a terabyte. And actually, you can say, well, I'm going to go from it, and just forget New York to Los Angeles. That's kind of close in inches. So I'm going to go from the Earth to the Moon. No, you still need 80. Do that 85 times for a trillion. The number of inches between the Earth and the Moon, I did the real calculations here, is 1/85 of a trillion. So let's try some cost calculation. Do you guys want to take a short break? Because I see some people come in and out. How about, 5-minute break? So back in 1978, back in the day, my Commodore PET PC, it had 8K of memory and it cost $12.50 per kilobit in 1978. Memory, actually that's the real price, I looked it up, and we'll show you this. And how I know that, because they had two models of this machine. They had an 8K model, and this is not 8 gig, okay? This is 8K main memory, and it had a 4K. The 4K version of the machine was about $400, and the 8K version was about twice the price, $795, I think. So, what's sought is how much did I pay for 8K of memory in this PC back in 1978. So we're going to use this unit cost of so many dollars per kilobit and multiply this out for 8K. Now 8K, now this is a good question. If people don't say K bits, K bytes, usually what do they mean? 8K in this case is bytes. Okay. So here we have 8K bytes, and this is the price per bit, and this is the number of bits per byte. So we get units canceling out, right? So we have bits cancel here, and we have bytes here, and we have K's canceling out. We end up with $800, which is the $795 that I told you about. What was the cost per bit in 1978 if converted to today's dollars? Well, there's this thing called inflation, right? And what is that? Well, everybody wants to get a little bit richer, so they raise the price every year as a few percent. It's not crazy like it used to be. When I first graduated from high school, if you wanted to get a mortgage, it was like 15%, and I'm not making this up, 15%, 13% interest per year. It was ridiculous. Now, interest rates super low, but you can look this up. There's a website you can compute annual costs. If you put 1978, you put 2016, it will tell you the multiplication factor. Okay, so that multiplication factor is actually 3.54. So we have the number of bits, right, and the cost is $800, and it would be about 4.3 cents per bit in today's dollars. Okay. So you're going to say, well, is that a cheap memory or is that expensive memory? Now think, it's hugely expensive, you're right. Suppose you wanted to buy an 8 gigabyte flash drive, which is like not that huge, right? And you're paying 4 cents per bit. You're going to be pretty poor by the time you get through the checkout at Best Buy. So I asked the question the reverse way here. If you could travel back in time, back to the future thing, 1978, how much would your 8 gigabyte thumb drive on your keychain, I have one because I bring my things to the lecture, be worth? Well, we know here there's so many cents per bit in today's dollars. You'd be rich, you know. Some people say, I would have bought whatever Microsoft stock, or I would have bought Walmart. Heck, you know, just bring a thumb drive. You're like Bill Gates. What's that?
It would be worth more than that just for the reverse engineering.
Oh yeah, I mean, like, well, they think you're an alien or something probably, and they put you in like a glass case, I'm sure too. But yeah, you'd be rich. So what's the cost per bit today? So you buy you can buy 8 gigabyte thumb drive for $4, okay, probably less, and 5.8 times 10 to the minus 9 cents per bit, okay, practically nothing. So we're going to see there's something called Moore's Law, which is getting near the end of its life, but because we double the density basically every couple years or so, we had 14 nanometer, before that was 22 nanometer and so forth. We've been able to reduce the cost exponentially as ECEs. A lot of really smart people worked on materials. A lot of smart people worked on the memory array design as computer engineers. A lot of smart electrical engineers on signal bounce and ground bounce and so forth to achieve these kind of things that we take for granted every day. Does that mean there's nothing left to do? Hardly the case. The basic takeaway that you guys can understand in a single sentence, in my generation, when I was an undergraduate student, graduate student, it was all about performance. We wanted to go from megahertz to hundreds of megahertz. Matter of fact, this original PC, what do you think the clock rate was? So if you have a 1 gigahertz, right, what do you think the clock rate was on this guy? It was a 6502 processor. It was actually in Nintendo and some other things way back in the day. It was 1 megahertz. Okay, so we were all about performance. Now everybody's about energy. We got the performance, we got a really good handle on it, we got good cache, we got good pipelining, we've got really cool things like branch prediction, and we made the processor about as fast as we can. We'll show you why, because of the speed of light. We're bumping up against some physical, the transistor is only 18 atoms across. You can't make it much smaller than that. So what is it about now? It's all about energy, okay? So we'll see this as we go through the class. So as I mentioned, the improvement factor, what's the improvement factor here in one human generation? This is my own real story, actually. My father bought this because he was an engineer. He did his master's at Syracuse. He was an electrical engineer, and he was into computing at those days. There was no PC yet, actually. But you can see it's a factor of what? Billion, trillion, right? Factor of 10 to the 10. Here, more or less, 10 to the 8, maybe. So we say today memory is free because it's so cheap relative to what we actually can use up, right? Using up 8 gigabytes is a lot of space, really. So let's try another example. Here is DDR4. That's double data rate version 4. We'll explain it in the memory module of the course. Memory modules. The memory chapter of our material. But here is a common design trade-off you have to make. You have module X and module Y, and you work for Google Data Center. And they're going to buy some new machines, and you're going to say, which module do I want to buy? And you have the option to use either. What is the best choice? As we pointed out, the best choice depends on what's the metric. So let's see some metrics. Which is the least cost per bit? Well, here I went to Newegg and I just scraped the screen and pasted it here. So this was $177, right? For what? 8 gig, okay? And this was organized as what? So this was 8 gig. It was RAM module. Here's the memory speed, okay? And this module over here, 16 gig per module, okay? And they're both the same speed. We'll explain all these quantities and so forth, speeds and megahertz and so forth. So what's the trade-off? Well, for $177, you get 8 gig, and for $283, you get 16 gigs. So without even crunching the numbers, which is cheaper per bit. Yeah, okay, oops. So here, right, this was $22 per gigabyte, and this guy over here is only 17. Module Y costs less. Which DDR4 module offers a higher maximum data transfer rate? So now we're looking at the megahertz specification. They're the same. Yeah. Both have 2133. There's different memory access speeds. We'll explain this later in the class, but the speed's the same. Now, suppose the average power dissipation is 5 watts and 8 watts respectively. Which design will minimize the cooling cost of the server farm? And that's a really interesting question. You say, well, 5 is less than 8. But what? Yeah, you need 2 of them. Exactly. Because it's the specification, you have to add 16 gig, because that's what they paid you to do. So if you're Google, you might actually want to pay more per bit to do what? Reduce your energy bill. Okay. So in this case, you need 2 modules. That's 10 watts total per 16 gig, and here's 8 watts for this here. Okay. So in this case, actually, the module Y is preferable. It's actually cheaper, and it's less energy consumption. So given all the above, which would you recommend? Well, now we're back to looking at all the metrics together. We look at speed was the same, so that's a wash, and then module Y is denser, so you only need to buy 1 of them. It's only going to occupy 1 slot instead of 2. It actually is consuming less power per bit as well. So module Y is probably a good choice by any of the metrics. Okay. But you can see the kind of trade-offs that you can make with these quantities and doing the calculations with these. Okay. So in this class, we're going to consider capacity, which is bits and bytes are the basic units, or units of bytes, kilobytes, so forth. Cost is always dollars. Speed can be in terms of time or rate. Speed and time is seconds, nanoseconds, milliseconds. Rate is hertz. What's the unit of hertz? Hertz is something per second, right? 1 hertz is something per second. So you guys got that. I won't write that on the board. But power, we measure in watts, microwatts. Okay. There's also energy. Energy is in joules. Don't worry, we'll have a whole module on that coming up later. Any questions on getting familiarized with these terms? You already know watts from physics, but what are the watts that we use? Well, a processor, let's suppose your desktop processor, if you have a pretty fast one, is it using milliwatts, or is it using, how many watts do you think? Hundreds. Yeah, hundreds. Like a pretty top-end gaming processor might be 100 watts. TDP is a power dissipation, and if you get much more than that, it's hard to cool it, because watts, there's actually heat energy. Every time we switch from a 1 to a 0, it means we're crunching bits, we're making decisions. There's some waste. What does that mean? It turns as heat. Okay, it's just like a mechanical system. If you ask me, if you have an elective for thermo, or let's say static, I guess you have to take statics. What do they give you a choice? Thermo and what else? Dynamics. Dynamics is good for the mechanical engineers, but I think electrical engineers can benefit from thermo, because we always talk about cooling and we talk about heat transfer, and just having an idea what those terms are can help you in your career. So the point of this module is to define these terms, but also define them in the context that we use them in as electrical computer engineers. Okay. We'll see more examples throughout the class. Okay, so we're wrapping up. I always end each module with the takeaways. The takeaways are things that you should know at the end of the class that you should actually take with you and kind of have an understanding. So the concept of computer organization is extending gates and programming together to realize a processor operation. And we're going to define that as instructions, which are the steps when software executes. That's the next module. And design of the hardware elements. We design them with gates, Boolean gates. And we're going to optimize hardware systems given constraints. The point is that the customer always tells us what the right goal is. It's our job to trade off. The design space is called design space exploration, DSE, how we can achieve those customer requirements in different ways that make the best sense. Sometimes designing hardware is better, sometimes it's not. What is it? Well, it depends if it's minimizing power or area or cost. Computing topics you'll be expected to learn in this class when you finish this course. It's still the first week. You can drop if you don't like it. But I think if you take this class, you have a pretty good grip on performance measurement. You talk about benchmarking. We're going to show you how to compare one processor to another, compare an iPhone to an Android, and what does it really mean? 8 cores. Is 8 cores twice as fast as 4 cores? Well, in the best day, but probably not most days, and we'll explain why. There's something called Amdahl's law. We're going to show you that. It's a real easy way to do some calculations. We'll design some arithmetic hardware. If you're an electrical engineer, you could probably find that interesting. Cache memory at the system level. We understand memory systems, and you really have an idea what these quantities are. We're going to use the MIPS 32-bit processor. That word width is 4 bytes, as we learned today. It's open source, it's inspired by, actually inspired ARM. ARM copied MIPS, actually. And using routers and so forth is something that you can understand in a semester, but also is practical. We're going to use the exponent rule throughout the course. So I suggest just memorize powers of 2 from 2 to the 0, which is 1, to 1k. And then, if it's greater than 1k, look for the power of 2 in front of it. So if somebody gives you 2048, you look at that and say that's 2 times 1024. So that's 2 to the 11. Why is it 2 to the 11? Because it's 2 times 1k, which should be, right, 2k, 2048, because 1k is 1024. So you don't have to memorize more than 1024, but recognize, 512, if 512 is sitting in front of k, right, that's 2 to the 9. And so forth. For larger prefixes, the Latin prefixes, when we work with bits and bytes, 2 powers of 2 times multiples of 10, right? So 2 to the 10 is kilo, 2 to the 20 is mega, giga. And then these frequently used quantities are huge. Actually, we take it for granted. We don't even think about these things, but they're really, really large values.